So what we were doing was the Fourier transform. Okay. So last time we did the Fourier transform, and also we said if we transform our image to Fourier, then we can filter it like we did in the special rule. Okay. So now we already discussed low pass filter. Okay, that's what is the low pass filter is supposed to be. Yeah. And now we discuss high pass, band pass, and other stuff. Okay. Okay. We discussed three types of low pass filter. Okay. So like in frequency domain, low pass filter is very easy. What is low pass filter in frequency domain? It passes the low frequencies, stop the high frequencies, right? But in image, where are the low frequency, where are the high frequencies? Yeah, so before doing shifting, and you just take a Fourier transform of the image. So where are the low frequencies? On the edges, okay? And high frequency will be in the middle. Get it or not? If you have an image, so the high frequency will be centered and low frequency will be at the edges, okay? However, as I told you, the most information lies in the low frequencies. So therefore, what we do? Shifting, okay? And because of that shifting, we get very nice low frequencies in the middle, and this will help us build a filter in a simple mathematical way. How? And I can just define a circle. Let's say I want to find a low pass filter. So I will define a circle here with the frequencies that will pass and that will stop. And this should be 1 and this should be 0. And multiply with the image frequency transform, I will get the low pass filter. Yes or no? Okay. So this is what I meant. Okay. Let's say I pass the frequencies less than d0. d0 is the radius of a circle. And after that d0, I stop it, multiply with 0. If I see the 3D view of this filter, this is the 3D view. And this is the top view. Okay, which is if I multiply this one with the image, okay, with the image, I will get what? The not image, the DFT of the image or the Fourier transform of the image. I will get what? Low frequencies, high will be stopped, and then I do the inverse. Similarly, if I just take a cross section here, or I plot it in a 1D, so I can get this. This is a low pass filter, and the frequencies less than d0 will be passed, and the other will be stopped. Okay, so this was one of the ideal, call it ideal low pass filter because this ideal have a very basic impulse response. Or the okay in the special domain we call the filter as the impulse response, right? And in the frequency domain we call it the transfer function. Okay. Kernel is for special domain. So here the DFT matrix we call it the kernel, but that is not the Fourier transform. That is the kernel of the DFT matrix. Okay. So we have to make these terms a bit careful. Okay. Yeah, this is, we already did that in special domain called convolution. So we have this modification. Okay. This is the good thing. That's why we are transferring image to the frequency. Okay. So what is D? DUV is the distance from the center here of any pixel U and V. Okay, so let's say I pick any pixel. Let's say change it. Let's say I pick any pixel here. So what is this term? This is the distance from the center. So if this distance is less than d0, what is d0? d0 is this. So less than it will be 1. Otherwise it will be so any pixel. I calculate this distance. If this is less than d0, it will be 1. Greater 0. Okay.
If we decide about the optimal values.
Yeah. So now the question is how to find out this. There's no optimal value, but what we can do is that we define what we call it the power. Okay. What is the power? We take the Fourier transform of the image, and the square of the spectrum is the power, and we decide that how much power we need inside or which we want to retain. Okay, so we calculate the proportion of the power that we want and the total power, and this proportion will decide how many power I want to retain. Okay, so based on this, I will get different circles. Okay, so let's say the radius of the circle is 10, 30, 60, this and this pixels. Okay, so corresponding to 87% of the power, or 93, 96, 98, 99% of the total that I want to retain.
Yeah.
First, I have to decide the d0. So I have to see that 90 correspond to which d0.
How is the formula?
No, formula is no formula. Yeah, first,
How much? I want 9%.
Yeah, this is what I'm saying.
I need to come up with the d0.
Yes, I have to. You have to come up with d0 that corresponds to 90% of the power. So you have to do some put some value of d0 here, just to see that have a loop, let's say in a program, and that you calculate whenever it reaches to. We start with let's say d0 minimum value, go to the maximum. What will be the minimum? Minimum will be 0. The maximum will be this d0, right? So start from here. Whenever you get 90%, you stop and use this thing. Okay, and this is when you have these percentages or different cycles. So you see that if you have smaller cycle, you have more blurry region. Okay, and similarly so on. Okay. But the problem with the low pass filter is if this low pass filter transform back to special domain, I get the response like this. What is the problem? If I take this low pass filter, transform it back to special domain, I get this thing. Or if I just take a cross section of that, I will get this thing. What is the problem with this? Now the problem is if in the frequency domain I am multiplying, so it means that in special domain I am convolving this with my image, right? So if I convolve this with my image, means that it's creating some ripple effects here. Yes or no? So it means that there is some issue with the ideal low pass filter. So because of that, I have to move towards Gaussian low pass filter, which is again a similar low pass filter. Previously it was like this, right? Now it's like a more smooth, like a Gaussian one. There are two advantages. One, there's no ripple effect. Okay. The other thing is in ideal low pass filter, this edge here I cannot control. But here, by specifying the dot value, the variance, I can have different type of curves based on my requirement. Okay. And this is 3D, this is the top view, and this is the Gaussian simple, I would say the formula, simple Gaussian formula. Right? Now this is okay for us for filtering from the filtering perspective, but the problem is again there's one issue that for a specific value of d0, let's say this one, I cannot control this slope for the curve. So in the Gaussian you have no linking effect. However, for more control on the transition between the high and low frequencies, about the cutoff frequency needed, then Butterworth filter is handy. So what is the problem? The problem is that for a specific value of d0, I cannot control this curve, that how much smooth it is. So that's why I will move towards the Butterworth filter, which is just nothing but 1 by this term, and this term, if you see, is like same as the exponential term of the Gaussian, okay, an inverse of the exponential. So if I plot this one, I have not only the similar to the Gaussian, but also changing this power. I am for the specific value of d naught, I can have a different type of curve. I can make these curves towards ideal filter or towards Gaussian filter based on the value of n. Let's say the value of n is higher, then it's more like an ideal filter, and if it is less, so it is more like a Gaussian. So I can make it smooth. Okay. So the performance Butterworth filter is somehow in between the ideal and the Gaussian. Okay. And if you see here, high value of n, I can make it more towards ideal filter, which again creates a ringing effect. For changing the value, I make it more towards Gaussian. Okay. This is there. Yes. For the filter, there are two things. One is you have a filter in time domain, a special domain, and you want the Fourier transform of that, and you have to do this. But here I am building my filter on in the frequency domain. I don't need shifting, right? Because I am building based on the concept that the frequencies are both under it. Finding these discontinuities because it will make the image smooth. So let's say there are some discontinuities in the writing. If I do the filtering, although it's not very good, it will become very blurry. But the main problem of discontinuities among the writing has been gone. Okay.
So if I sharpen it again.
Yeah, you can do some sharpening. Also, you can do some instrumentalization to make it better. Okay.
If we sharpen it again, directly sharpen, then it will be like the previous one.
No, if you do sharpening of this one, so let's say what was that? But for that image, so it will become better. Similarly, let's say you want to smooth out the image. There are some wrinkles here, and you can want to remove them. Here as well, there's some error of the printing. So if you smooth it, you can remove it. Okay. So these are the summary. We have ideal low pass filter, Butterworth filter, and Gaussian, three main type of filters. Okay. So since you have three type of low pass filter, we have three type of high pass filters together with some other filters as well. Okay. So how to make these three low pass filter high pass filter?
1 minus d.
Okay, so I just make it 1 minus low pass filter, and I will get the high pass filter. Okay, and so here in frequency domain it's very easy. 1 minus low pass filter, you'll get the high pass filter. So 1 minus ideal low pass filter, you get this thing. Okay, 1 becomes 0, 0 becomes 1. For this again the Gaussian one. Okay, and 1 minus Gaussian becomes high pass Gaussian. Similarly, Butterworth filter, 1 minus Butterworth filter, and then after simplification you get this. Okay, and these are the frequencies responses in 3D. Size or to make sure that okay, so these are simple ones. But if you remember, we have for the high pass filter in the special domain for the types what we discussed in special high pass. So one was the Laplacian, okay, and the other was the unsharp mask. Okay, last week sometimes we call it high boost filtering because of that constant in the process is more than one. You can call it high boost filtering. Can we do these two in frequency domain? Because these three were not really possible in the special domain. Okay, although one thing we can do it to find these in frequency domain and transform it to the special domain, but which does not make sense. But in the special domain we have these two. Okay, so this is the extra advantage that we have some very basic filter in the frequency domain, and let's see can we do these operations in the frequency domain or not. Okay. So one again, these three are the same three filters that we did, the ideal low pass filter and Butterworth filter, but now since it's high pass, so the response is inverse of that. Okay, so again this is I think the ideal high pass filter, Gaussian filter, Butterworth filter, and this is again the same thing with different d naught. Okay, so if you increase d naught, what will happen? If you increase d naught, high pass filter, what will happen?
More widely.
If I increase this one, d naught, so we are passing the frequencies. Which frequencies we are passing? Side. If I increase, it means that we are stopping most of the. Okay, so that's why it's become more fine. So this is another example of high pass filtering. If let's say you have a thumb compression here, and I take the high pass filtering, and then after that I do some thresholding, can make it black and white. You can see this is much more clear than this and much more sharp. Okay, so for the high pass filter again, there's three types basics which we already covered. This is one of the example of high pass filtering. You can also try for other filters. This is only I tried it for high pass filter. You can try for low pass filter. You can try for Gaussian or okay. So what I did, I took an image. Okay, I want to find the ideal low pass filter with d naught 0.5. What do you mean by d naught 0.5? Circle has a radius of 0.5. So inside 0.5, I make it 0. Okay, outside 1. Okay. So first I have to do, as your question, first I have to make it to the center, shift it, and then I take the DFT of the image. Okay, this is now the frequency transform of the image. Fine, and I think the steps are very clear. -1 is just multiplying with this matrix, term by term multiplication. Okay, when I in the images when I'm talking about point by point multiplication. Okay, after that I take a discrete Fourier transform. Okay, and we already did that. If you have 4 by 4 matrix, we have 4 by 4 kernels. Okay, and once I multiply them, here I get this. But here the multiplication will be 1 by 5. No, because this is a transformation. So make sure this is not 1 by 5. First here I'm taking the Fourier transform. I'm not taking the filter. Okay, so fine. After that I have to calculate DUV. What was DUV? That was equal to distance from all the except from the center. So what was the formula for that? This was the formula, right? Remember that? Okay. So what is m or n here? It is 4, right? 4 m and 4 n. M n, right? Okay. So now u and v can take how much values? U and v are either here like 0 0, okay, 0 1, and 0 2 0 3. Similarly 1 0 1 2 1 3 and so on. So it will go from here to here, right? Like this. Okay. So I have to calculate this value for all the pixels values, okay? And I get these all values. If I want to find the D matrix, I will get this thing after putting all these values here. It's just a calculation. Simple, just put the value in. Okay, fine. Now the given is 0.5, means that less than 0.5, 0. Okay, so I have to see the less than 0.5 is only this term. The others are not there. So I put 0 here, 1 here. Yes or no? Okay. After that, this is a high pass filter. I multiply with this should be f. Okay. So with the image multiplication here. Okay. This is now again this is the term by term multiplication. When you're doing the filtering, this is a one by one multiplication. So it will not be matrix multiplication. But if you are doing the frequency transform, then this is regular multiplication. Okay. So now after this is now filtered image. So in order to get back, again I do the inverse Fourier transform. After getting the inverse Fourier transform, I have to make sure that I do again the shifting. So shifting, going back to shifting, again have to multiply with this. Yeah, but this is for the high pass filter. Let's say I give you for the low pass filter, or I give you another Gaussian filter. Okay, so what will be the kernel for the Gaussian filter for the Butterworth? Okay, this is the matrix. So I use this equation to find HUB, and the rest process will be same. Similarly, for the Gaussian, I use this matrix, and the rest process will be the same. Okay, so you can try yourself for the other filters. For the low pass, for the high pass, we will do band reject filter. Also, I will do the Laplacian filter. Also, I will do the unsharp masking. So you can try all of them. Now, as I discussed, we have 3 types of filter in the high pass filter, which are the filtering, which is the basic ones. Now, I have to see that what the Laplacian filter and unsharp mask look like in the frequency domain. For this, I have to first find out what is the Fourier transform of Laplacian. Okay, because what is this? This is a filter applied on the image. What does that filter look like? A difference. If you remember, x-axis we took the difference, y-axis we took the difference. Okay, so this is a filter convolved with image, right? So I have to find that what this derivative will be in frequency domain. If I found this in frequency domain, I can find the filter in frequency domain and I multiply it by image in the frequency domain to find out what should be the filter will look like, right? So using the properties, this is given in table number 4.4. The second derivative is equal to partial derivative has the, let's say this is in the frequency domain is equivalent to this thing. Okay, the partial derivative is this. Okay. In the Laplacian, you have second derivative along the x-axis and y-axis, right? So if the Fourier transform of the Laplacian function will be what? This nu plus j2 pi b square. Yes or no? What will be the Laplacian, the Fourier transform of this? That will be equal to j2 pi u square plus j2 pi v square. Okay, which is equal to. So it means that this is my filter now. So in order to apply Laplacian on the image, I have to multiply this with the frequency transform of the image. Okay, this is equal to applying the Laplacian on the image itself. Yes or no? Okay. So now, now another problem that this one is not centered. Okay, this is just taking the Fourier transform. So if I take the Fourier transform, I have to make it as center. In order to make this as a center, I have to subtract from the middle one, and p by 2 and p by 2. What is p and q? P and q is length on x and y axis. Okay, which is m and we call it m and n as well. They are saying p and q is m and n. Okay.
So it's moved the
origin to the center.
okay.
P and q here are, like for example, this is, it was actually in our case m and n, right here. Okay, so this is p and this is q. So let's say I want to move this on center. So this is what, n by 2, and this is okay. So in order to, I just subtract it. Okay. So what is this? This is again previously we defined it d square. Yes or no? Okay. So I can write this whole term as minus 2 pi square d square ub. Okay. Now in order to apply the Laplacian and to get equivalent to the time domain Laplacian filter, I multiply this filter in the frequency domain with the frequency domain image, and then take IDFT inverse, get this. So in order to perform the Laplacian transform in the Fourier domain, I do this and then take the inverse to get back. Okay. Why I'm doing this? To save my computations in other image. Okay. But we did not end here, because when you remember you applied Laplacian, it would give us the edges. It did not sharp the image. In order to sharp the image, I add that. Okay. Yes, to the original image. So we can do all this step in one step in the Fourier transform. How? For example, if I write this in a Fourier domain, I can write this is the Fourier transform of the image. Okay, and this thing in the previous slide we have seen that this is equal to this. So if I take these two, add them, and take IDFT, I get the sharp image in the special. Okay. However, still we can even simplify it, taking the common term FUV. Okay, I get this thing, and what is this one? In the last slide we have seen that this is equal to this. So if I do this thing, take IDFT, I will get the sharp filter equal to this special. And why am I making special to say computation? Because of the condition. Okay. There are some notes here because when we are doing the Fourier transform of this and this, because of some computation, some constant terms, they are not in the same scale. In order to make it the same scale, we have to normalize f of x between 0 and 1, and the filter, Laplacian filter, minus 1 and 1 before we add. But this is still very less important. Just keep in mind take it also. Okay, fine. So it is the same image that we saw in chapter number 3, but this is done by using Fourier transform. You get the same result. The only thing we will have is save the computations. Okay, so you can see that it's being sharp. The other sharpening filter was the unsharp mask, and we also sometimes call it high boost filtering. So unsharp mask, if you remember, I take the difference. First I filtered it low pass, subtract from the original image to get the edges, and after I get the edges, I add the original image to highlight the edges. Now why it is called high boost filtering? When k is greater than 1, it means that I'm boosting the high frequency. If the k is greater than 1, we call it high boost filtering. Okay, so that's why this is another name. Now this, yeah, you can choose k. Okay, now The same thing I can do in frequency domain. What is first I have to low pass the image. So in order to find the low pass filtered image, I have to multiply image Fourier transform of the image with the low pass filter, any filter, ideal, Gaussian or Butterworth. Okay, and taking the inverse will give me the low pass filter image in special domain. Okay, so what is now this? This is the image but minus the low pass filter. So I can write this as frequency domain image minus low pass filtered image in the frequency domain, and then taking the IDF get the special thing. And after that, I have to do this step. So this step is equivalent to taking the yeah. So if I can just take the f, first they did it like in one step. We can have f of ub, okay, plus k and this term. Okay, so I can take f of ub common and I get this. And this is what is this? This is low pass filter. One minus low pass filter is high pass. So in order to do the unsharp mask and high pass filtering, I have to do this operation and take the IDFT to get the unsharpening image in the special. Okay, and this is what it will look like. You have an X-ray, which is not very clear. I did the Gaussian low high pass filter. Okay, and then I did the high boost filtering. For high boost filtering, I used k greater than 1. Still, it's good, but not better. So what I do, I did a histogram equalization as well. Make things okay. No, thresholding is just like we did it like black and white. Okay, so we just threshold it like on some values. Above that, we make it black or below white, black and white, just black and white. Okay, here we did the histogram equalization. Now you see why I'm doing here thresholding, and it depends on again hit and try type of thing. Here maybe they did it thresholding, but it didn't work. Okay, so they apply another stuff here. Okay, and also maybe you can first plot the histogram, see if the histogram is computed on small portion. Okay, apply histogram equalization to make it flat and it doesn't. Okay, so here now what we are left with. We did low pass filter, high pass filter. Again, we have seen which is between one minus low pass filter. In this table now making more sense as compared to before I just showed you, but we did not discuss much. Okay, and if I take the IDFT of this, I will get this thing. So what is band reject filter? Band reject filter is take the band and that will you reject others. You will. Similarly, the band pass filter is opposite that. Okay, so this is the band reject filter of ideal band reject filter. Then we have Gaussian, then we have the Butterworth. Okay. So now what is left? We have low pass filter, we did high pass filter. So if I do band reject filter, I think we are done with all the filters because band pass filter will be just 1 minus band reject. Yes. Okay. So in order to do that, you can take this expression. Having one low pass, add to a high pass, and based on the overlap, you decide that how much band I have to reject, the width of that, right? So if you do that, you get this ring. Band reject filter, band pass filter, you have this thing. Okay, you pass this band, you reject this band. This band reject, this is rejecting this band, this is passing this band. Okay, now cross section wise, this is band reject, I rejected this band and pass this one. Similarly, this is again a simple Gaussian, but here I'm not completely rejecting these frequencies. Here I have some frequencies, but I just make it low, but did not completely reject it. Okay, and similarly, this is the Butterworth filter. Okay, how it will look like if you apply this equation, which I already showed you. Do some apply this equation, and with some manipulation, we come up with the 3 variants of band reject filter. One is ideal, one is Gaussian, and one is a Butterworth. Here, if you see, it's very easy. Like for example, C0 is the center here, and then this is the width. C0 minus W by 2 and plus W by 2. Okay, so you reject that one, and otherwise you pass that. Right here as well, you have C0, okay, and W. But this expression, how it comes up? Take to filter, low pass and high pass with different cutoff frequencies, and try to simplify your integration. Okay, and similarly here as well. This is again. One of the filter which is called the notch filter, and this again variants of the same thing. Okay, now for example, if you have a picture of a car and you see here that right, you have some periodic distortion, periodic sinusoidal. Okay, so if I do the Fourier transform of this image, I can clearly see that there are some. You see this one? Okay, there are some periodicity because here it is periodic. In the frequency domain, it will be pulses at that point, right? On the frequencies at that point. So these creates these frequencies, right? Which is very clear, right? Because the actual image will be a low pass filter, low pass image, right? Okay, so I know that this information belongs to the original image. Okay, whereas this periodicity are the frequencies that are appearing here. So how to remove this without affecting the image? Yeah, so what fine, there's a term notch, but in general, what we have studied how to do that, I can define a filter. Let's say I have to remove this. So it means that I should define a high pass filter, which should be in the middle. In the middle, it should cut off, right? And then, but I don't need this one. A high pass filter and a shifted version of high pass filter. The high pass filter shifted here. Any 1, 2, 3, 4, 5, 6, 7, 8. We need, right? 8 filters high pass, but shifted in different locations. Again? Yes, somehow manual as well. Okay, so but I need a notch filter is nothing but high pass filters located in these locations. But if you see these locations, these are correspondingly opposite to each other, which makes sense. If you have a sinusoidal, I get 2 impulses. Yes, so this sinusoidal, so I get 2 corresponding impulses here. Okay, then 2 here. Okay, and then 2 here. So if I take this one, I say okay, I have these 2 pulses here, and then the product of these 2 and the product of these 2, and similarly these 2. Okay, so this is what this is the high pass filter. This is the high pass filter, but a shifted version of this. So shifted version, these 2. Shifted version of high pass here and like this. So I take the product of all of them to get this filter. So it means that I have the combination of high pass filter, nothing else. Okay, get my point now.
If you write all the differences about the right corner, how do I know these unknowns? Maybe this is not the picture.
Here it's right there, but there are a few things that you can connect them. One is, as I already said, the actual image is a low pass filter. Okay, so I know that whole actual information is here, right? The other information is not actually related to the image. Okay, this is one. Second, because I can see from the image that this is a periodic, okay, cosine cycle. So it has certain frequencies, okay, which is very clear that it's repeating itself because of this d naught. And the third is definitely hidden triangle. Okay, so first you have to connect the dots that these are the ones, okay, and then you process the rest. Again, yes, you can use the but it will again who's like this? Yes, so it will blur the image. So notch filter is better because we are just selecting the specific frequencies, not the whole thing. Because as you mentioned, might be there is, for example, if you see here, can you see this one? This thing? This thing does not belong to the image, but the image itself. Okay, so if I do a low pass filtering, I'm cutting off this part and this part, which might be because of this thing. That's why this notch filter is good if you are selecting some filters, not all. So the example I showed you at least think that how you can modify it for the other filters. Okay, so it will clarify your mind how to apply these filters on the numerical example that I showed you. Where was that? This one. This one. The only thing we will change is the filter. The other things will be set. We finished the image enhancement part for special and the yes, yeah. Now with chapter 5, I think it will be even more interesting because it's related to image restoration. Definitely we will see that how the images are degraded and then how to restore it. Okay, in time domain, in spatial domain, and also in frequency domain. For that, we will discuss some noise models and the noise reduction techniques, and then how to estimate some function. But I think this will not discuss in detail. Okay.